Ladies and gentlemen, hello and welcome to the KEMET webinar on our gas and flame sensors. My name is Alexander Nebel and I will moderate the webinar today. We are very pleased that you find the time to join our webinar. Presenter today is Michael Freitag, our product manager for magnetic sensors and actuators. Hello Michael, thank you for presenting again today. Please tell the audience shortly about your role inside KEMET and then you can start directly with your presentation.
Hi Alex, good afternoon. Yeah, my name is Michael Freitag and I'm responsible for the product management for magnetic sensors and actuators in Europe. And today I will talk a little bit about a new sensor range, I would say. I wouldn't say that it's only one product. And from that perspective, I'm happy that you found the time to join the webinar today, and let's go through this. At the moment, we are in a time where we are building up these sensors basically in the system. I mean, some of them are already released, and I will talk about this a little bit later in the webinar. And some of them, they will come this month, next month, so very, very close. So first of all, the pyroelectric infrared frame sensors as an introduction. I mean, it's made for a wide range of applications, and I will guide you through the principles, some typical information applications, and how to avoid infrared interferences. And coming more to the device itself afterwards, I will give you a summary of stability of the device, the energy consumption, the available communication protocols or options, and to finally give you a few bits of the data sheet just as an outline. Some of the data sheets, as I said, are already uploaded in the internet, and some of them will follow in the next few weeks. There is also some alternative or optional products available. I mean, we are more or less releasing these for the main, let's say, application areas. But if you have a certain application where you try to find some kind of solution how to measure, I mean, let us know, because we have a lot of let's say customized opportunities there as well. First of all, talking a little bit about the detection principle, the basics. So the infrared light belongs to the electromagnetic radiation, and it's situated between the visible light range and the slower microwave band. So the sensors are optimized for mid-IR radiation. That means that it is between 2 and 14 micrometer wavelengths. And the pyroelectric effect of the PZT material, ceramic material, is there's a change in polarization inside the material with a presence of infrared radiation. So most gases and liquids have specific wavelengths absorptions within this mid-IR range that can be used for, let's say, selective medium measurements. I mean, could be gases, could be liquids as well. When narrow optical bandpass filters are used between the medium and the sensor, of course. So I will give you some guidance about this, how this works on the next couple of slides. So there's basically two principles of how to sense this. The first one, the easiest one, let's say, is a kind of a passive sensing. And it's possible when the medium itself is radiating IR in a certain area and is hot, so that it can be a body, a human body. I mean, we have also proximity sensors and such that work actually very close to this, or it could be a fire in example. So the sensor acts like a camera, and the sensor sees through its built-in filter a very selected and narrow spectrum of the infrared. That can be used for identification of a certain medium of the content, let's say, in an area. And usually a medium is not radiating IR itself, but when the specific absorption of individual wavelengths of the medium can be used with an IR filter, similar to an IR source, similar to a light bulb. So that would be like the active kind of IR sensing. So that means there's an IR source, the medium in between, and then the same setup like on the left side. And in this example, here we use CO2 as it's very often used, and it's also very relatively easy to detect this as it has a high signal, let's say, which can be used. The passive detection, the CO2 is in a combustion, like a fire, and the active detection is basically, for instance, like a breath analysis, where the CO2 is part of the gas inside, and in some application, and then come later to this, it's important to see the content of this within the given mechanics. But every medium has a certain emission or absorption fingerprint, let's say. So that means, and basically, and you can see this here on the graphs on the right side, the absorption is really in a very narrow wavelength area, which is around 4.3 micrometer. So that means if we have a filter in the same area, in the same spot, I mean, then we can really easily measure the content of CO2. On the left side, as this is kind of a passive principle, I mean, it's like CO2 from a burning environment. So it's hot, and then it's emitting these kind of infrared radiation. So again, the same filter, but then you don't need a light source, right? Or an infrared source on the other side. I think that's relatively logical. So as an introduction, I mean, I wanted to start with some kind of possibilities. What is available, let's say, to measure. And when we look first again on the right side on the passive detection example, then there is this CO2 coming from the flame, and it emits this infrared radiation, specifically with a peak around this 4.3 micrometer. And this could be used to detect the flame with having this optical bandwidth. And then you have a sensor. And here in this case, I've chosen an analog one, which can detect then basically the signal or the sensitivity, let's say, of these specific IR area of around 4.3 micrometer. And the other thing is, I mean, this flame here in this example is a pretty stable flame, but you see this from, let's say, typical fire, for instance, that the flame is usually flickering. So you have like a changing, let's say, signal or a kind of energy of what is pulsing, basically. And the sensor is so quick that you can even recognize if there's some kind of flickering or if it's a constant flame or something like this. So there's a lot of potential for applications. The active detection, this is, for instance, in a breath analyzer, same CO2, but it doesn't radiate, of course, because it's cool, but it absorbs at the same frequency or the same wavelengths, basically the IR. And in this case, we have, as you can see on the drawing, I mean, there's an IR lamp or a source, and there's like on the other side of the, let's say, tube, there is a sensor. So, and then it's representative for the content within this kind of tube, how much CO2 is basically in. So that means the more CO2 is in, the less signal the sensor would show in this case. So it's exactly the other way around. Then when we come in general to application for flame and gas detection, I mean, for gas detection, that could be used in emission management, in climate control things where there could be some leakage of basically of the medium, of the gas, what is inside. Breath analysis for medical diagnostics, and the bold ones that I have basically made here in bold on that slide. I will go a little bit more in detail to this. Climate control devices in general, also by the presence of, for instance, CO2. I mean, you can detect if there's some kind of humans in buildings or something, for what kind of alarm buildings or alarm applications or something like this. And also in the greenhouses, if you want to accelerate the growth of plants, I mean, you can also use a higher CO2 content than it is usual in the ambient air to kind of accelerate the growth, right, from the plant. So that could also be monitored basically with having this kind of gas detection. With flame detection, which is more the passive side of it, it's more for sensors that are used in combustion applications, sometimes for fuel control, fire detectors, where basically the flame is not detected, but the CO2 which is coming from the flames, which we call shadowless. I mean, it's the safety systems, of course, and also when it comes to a forest fire or something like this, there's a possibility to use this kind of sensor for protection or for detection, basically. And then later on, of course, that firefighters could come without that anybody has notified it, because the fire was already so small, right? First of all, as I said, a little bit more in detail of the breath analysis, why this is helpful. There's a certain application which is called capnograph. And basically, the capnography is monitoring concentration or partial pressure of CO2 in kind of the inhale and exhale gases. And and this is used usually during anesthesias or intensive care. And I mean, currently pretty prominent example is like within these medical ventilators at intensive care stations. I mean, they are also monitoring basically the CO2. It is visible in this case, the blue left curve, that given the short response time of the sensor, a pretty accurate measurement of the breathing cycle can be gained, as CO2 has a high absorption. And depending on the IR source, of course, it can easily be half of the full scale of the sensitivity that can reach a signal to noise ratio of around 250, which is pretty nice. And here the IR source is pulsed at 10 Hertz. So in 100 millisecond cycles. And due to the fast response time, the pulse duration does not need to be half of the main information is securely provided after 25 milliseconds. So because the sensor is accurately measuring from like 12 milliseconds onwards. So that means when you pulse basically the IR source, then you don't need to spend the whole energy of the whole cycle. So basically you can shorten these, and that means that also battery-driven applications could be potentially feasible. When you look at this, and I'm not a medical guy, I'm not a doctor or something, but basically on the curve that is the outcome of this measurement, you could easily read the frequency of breathing, and you can also see the content of CO2, of course, one of the main reasons. And of course, you inhale mainly oxygen, you exhale CO2. So it's basically, you can make some conclusions about the medical, let's say, situation with a certain person there. Okay, a second example I want to give is like the fire detector based on CO2, which is shadowless, as I said before. There are some systems which are operating cameras, but those would fail to detect fire in like shadowed areas that could occur to some kind of objects which are in between. As you can see on the drawing, I mean, the flame behind this gray kind of rectangle or whatever, could be a table, could be a desk or something like this. I mean, that would be invisible for this detection method. However, if we would add a pyro add-on, let's say with an additional sensor from the range I'm introducing here, and basically this pyro sensor is not seeing the flame itself, but it sees the hot gas which is emitting from the flame. So that means you can see these kind of black kind of lines. I mean, the sensor would see this, and with this, there could be an evidence of a fire. And the directivity is pretty high. So it's also, I think I saw something that depends, of course, on the custom application, but I saw some kind of ranges of up to 65 meters or something from detecting a fire. So that's quite a big distance. And also what can be done, I imagine it needs to be a little bit closer then, is to analyze, let's say, flickering. So that means, of course, there could be some kind of disturbances from other sources, probably sunlight or something like this, which could interfere with the current, let's say, passive sensing. However, when the customer can basically then analyze the flickering, he can be more sure that it's really coming from a flame instead of having like a malfunction or a wrong alarm in this case. Right? Okay, then the topic equalizing interferences. As I said on the last slide, I mean, there could be some interferences. There could be some other sources that radiate IR in the same spectrum where the filter is trimmed to and can compromise the results. And as I said before, I mean, could be sunlight, could be halogen lights. Human motion could be, I mean, your body itself is also radiating IR, so it could be also an, let's say, disturbance. And also hot materials could be an issue. Think about gluing steel or something like this. I mean, it would be something like this, or even other sources which are hot, or also welding, of course. And there could be some kind of rejection channels that could be important to avoid these false alarms. And basically, there's two possibilities for this. For very much known issues, I mean, we have already filters in place which are limiting the interferences. So that means you can order this kind of filter with a sensor with a specific filter, and then you would have a better, let's say, behavior. On the other hand, there's a possibility, as I mean, not launched today, but within the next few weeks, we have like multi-channel sensors, which can be trimmed to different kind of filter behavior. So that means when you look at this example with CO2, I mean, in this range, there are other sources. And if you think, oh, the sunlight could be an issue, I mean, then of course you can also take a filter in another wavelength area, even like narrow, like the one that is shown there. But if there is sunlight to a certain extent there, then you can see, okay, also in the window of this CO2 filter in that area, that might be sunlight, which is disturbing, right? So you have, you can do dual sensors, or you can use quad sensors. I think that's the most what we have in one device. But anyway, that will give you some more, let's say, selectivity when it comes to the individual gases you want to spot in this, or measure in this range. Then the other thing is, it's a pretty reliable detection method. Easy adoption, I would say. I mean, there's no chemical cell or no chemistry involved. There's no, let's say, huge lifetime dependency. It acts pretty linear, and it's not so much disturbed by other ambient conditions. I mean, when you look at temperature, ambient temperature, in a full range from -40 to 85 degrees C as operating temperature, I mean, the difference in the signal is relatively low. Here in this case, even with the with another knowledge that the temperature here also influences, of course, the infrared source, so the let's say the light, and this is even inside this measurement already. So the sensor itself is even more linear or uncompromised, and it doesn't need to be cooled in that way to keep this kind of linearity. And then from timing, so means time of use of these devices, I mean, we didn't see any degradation over like 14 years or more. So that's kind of, it's very long life product, which is probably good for industrial and medical equipment and things. So there's no need to change sensors regularly within a given application. It's very long-term stable. And then vibration and shock, I mean, There is it's pretty precise. I mean, it's a robust assembly structure. There is not a lot of sensitivity to mechanical or thermal shocks. Also, talking about electrical shocks, like a little bit of overvoltage or something like this. I mean, it will recover. I mean, within like less than a second or something. So it's pretty reliable and fast, and it doesn't need any warm up. I mean, the sensor itself, or the PZT thin film, is very small, so that's why it doesn't need to have a long warm up time. So the, let's say, calorific let's say capacity is very small, so that's why it's quick and also responds without a lot of warm up time. Energy consumption, I mean, depending on the sensor version, we have digital and analog ones. With the digital ones, we can do a little bit more deviations. The analog one is as it comes. The supply current consumption is on a relatively low level. So the passive one is roughly at 65 microamps at 5 volts. And the digital ones are usually at 33 microamps in operation, but they also have like low energy modes and even a standby mode, which can drop down the current to 1.1 microamps, I believe, when it's in a standby operation. And as a response time is short, I mean, it's the other possibility for reducing the energy that is needed. On the upper end, it's more like the passive way, right? But on the lower end, on the lower chapter here, it's more the active way. So the response time is short. And from that perspective, the IR source doesn't need to be on very long time. So that means the on time can be shorter than in usual circuits, where you need to have a little bit of longer warm-up time. And sometimes, depending on what you, of course, relate this to, but it's a potential of using only 1/10 of the emitter power in an active IR application for gases or media than when you do this in a different way. So there's some possibility for also battery-driven applications that also can then operate for a longer time. Okay, then communication and the option that we have. The analog one is coming in a TO39 case with 3 pins. So you basically have supply voltage, ground, and then the analog signal. And it's in current mode sensing. It has a responsivity of like 150 kilovolt per watt. So it's pretty high, and the stable frequency response up to like 100 hertz or something. Ultra short time of measuring, so within like these 12 milliseconds. High dynamic range, so it's high signal to noise ratio. There's an integrated operational amplifier. So that means in most of the cases, you don't need to have an additional amplifier afterwards. So that is usually enough to have a strong signal. And as I said before, so rapid recovery times from any issues that might occur. And then we have the digital ones. They can come into a TO39 case as well with 4 pins then, or in an SMD package. And in an SMD package, there's a little bit more on possibilities because of the connections in the 4-pin version. I mean, we have limited down to the really necessary ones, which is first of all an I2C interface with and in the SMD package we have an additional analog output. The sensors itself, they have integrated the special filters and the analog digital converters, the buffer, the clock, and also the DC-DC converter, and the power saving modes and low power consumption. I mean, this is when which you can enable from let's say your application, and it is also adjustable. So the gain is programmable and digital filtering as well. So yes, kind of a few things you can really adjust towards what you need in this case. little bit an overview about the QFC series, some facts from the data sheet. To start with, the QFC series has the largest aperture size, so it means it has the largest window on top of it, and also the bigger, let's say, PZT area below it. That means that it has a higher sensitivity, but on that a little bit slower reaction time or response time. The detection angle of the QFC series is around 100 degrees. So if you mount something in application into a corner, I mean, you should be able to observe a full room when it is rectangular or quadrupolar. And the supply voltage is rated at 5 volt, but it should not be higher, really not be higher than 8 volt, and not be lower than 2.7 to operate properly. And the analog signal is generated around the half of the supply voltage. If you take the 5 volt, then basically this is like in the 2.5 volt at let's say the 0, the neutral, and then it goes up and down depending on the recognition from the outside. And the sensor can be used at ambient conditions, as I said before, from -40 to 85 degrees C. You can see the mechanical setup on the top right corner. It has a diameter of a little bit more than 9 millimeters and is 3.8 millimeter high, so it's relatively small in that case, but again, also very reliable in terms of measuring. And then the second option that we have already, where the data sheets are loaded already, is a QFS series. And this is like a digital SMD sensor, so that is not yet released in a TO39, but this will come. With a digital communication, this IA2C standard, and the sensor element is a little bit smaller, so the responsivity is a bit less, but with the advantage of having a shorter reaction time, means an increased speed of measuring, which is then around 10 milliseconds against the analog one, which is around 12 milliseconds. The parameters of gain, sampling rate, digital filtering can be adjusted, and also the sensor can be switched into a low energy or even standby mode. And then with standby, you get down to like this 1 microamp. So the detection angle is a bit compromised to 90 degrees, which is still, I think, rather big. But in that case, we also offering a different set of filters, which are sometimes more focused on the middle, let's say on the middle area of the when there are rays coming in straight. Some of them are more equalized for the whole sensor area. So there's a couple of options, and if you need some kind of recommendation for your application, let us know. And then we have also a modular sensor, which we offer. It's not in a picture here, but basically it's a small PCB, which can be attached by a cable towards any PCB you want to use. And with this, you can do testings or you can do evaluations without really putting the sensor itself on your own board in that case. And there's also a software kit, an API available for changing the parameters and also to implement this properly in your software solutions. Okay, finally, here's there are specific options available, and I wouldn't call it a roadmap because everything is already physically there, just need to be uploaded in the internet basically. And if you want to learn more about this, just get in touch with it. However, to give you an idea, there are arrays of sensors available, which have also a very small size and almost the same parameters like the introduced single sensors, let's say, but those could be used for spectroscopy of the mid-IR range for more difficult mediums. So could be also for food analysis and things like this, milk and such. So there it's really better to have the whole range. And this could be done also in basically two different scenarios. One is with a prism that you, with a prisma, you can separate the mid-IR range across the sensor, which has like no filter, because the prisma would do this. The other one is that is like kind of a linear filter, let's say, so that basically the individual ray which will come will will create a responsiveness on a certain area of the array, so that you get at least, of course, a signal. And then I talked about CO2 the time before at the beginning, because those are the most, let's say, prominent examples. But as you can see in the middle, there's a little table that shows a certain absorption behavior of a selected, let's say, gas or medium. And you can see there's different solutions for like CO for any hydrocarbons, for water or steam, let's say, for methane, for any nitrogen or sulfur containing gases. I mean, it all depends on if they have like a special behavior, these gases, in the mid-IR area. And if this is present, I mean, there could be a solution found with a certain filter, and also with a certain kind of layout, depending on if you want to more have it analog or digital. So come and ask if you need this. On the right side, you see what we have already released. I mean, from that TO39 case point of view, the single flame sensor for in analog, and I mean the digital is there as well. And then what is coming is now the gas sensors, and there you can see on the screen the single ones, the dual ones, and quadruple ones, which are able then to detect different absorptions or different IR through different filters. I mean, it's not so visible on the screen so much, but they have different colors, as you can see, the filters. So they are there for different gases, or to avoid malfunctions because of some kind of interferences from the outside. And then, yeah, last but not least, conclusion and questions. So what I said before, I mean, we have basically a fast and reliable measurement with these sensors. It's a wide range of applications for what it could be used for: flames, for gases, for food. It's a relatively small sensor size. Actually, I think it's the smallest on the market, at least the digital one. And then it has a low power consumption, and it's usually an easy integration, specifically with the I2C communication option available. I mean, then you can really use the digital signals straight without any disturbances of like wires, for instance, that are connecting an analog sensor when it's a little bit further away from the application or such. So in this case, I think it's a very good product, and hope that because we just launched it, hope that it will have some interest in the market and also with you. And yeah, and I give back to Alex now.
Was very interesting. We will publish the presentation after this webinar. And to all attendees, please watch also our webpage for the next upcoming webinars. Michael, thank you for presenting today, and I hope to see you soon again.
Thank you, Alex. And just as a last comment, I mean, if you have any questions, I heard there were a few. I mean, you can also send this straight to me when you have afterwards some questions. I mean, my contact data is there. Send me an email, and I will try to answer everything what is possible. Okay, thank you for attending, and have a great day.
Thank you, and goodbye.